So as we saw some time back, signals can have infinite energy. Very simple example, all periodic signals. Not only periodic signals, just take even the step function. So what is the step function? It goes from 0 to infinity, and the magnitude x of t square at every point here is 1, and the energy of the step function now turns out to be infinity, right? So the step function has infinite energy. All periodic signals, real valued or imaginary valued, can have infinite energy. So this is the problem of having energy as a measure of a signal. Sometimes it can always be infinite. So in order to take care of this, we define what is known as the power, which is basically nothing but the average of this energy. You compute the energy in a particular time window and take the average. You just take the average of this and then say that, okay, this is the average energy across this time. And then you keep expanding this time window. It is as good as saying that I'll compute the energy over the entire time window where the signal exists and then take an average. So this is what we refer to as the power of the signal. And whenever the energy is finite, that is, the signal is an energy signal, the power will be 0. That is simply because you are having this average computed from over minus infinity to plus infinity. So as the signal period increases and the energy remains constant, which is finite, then this average tends to 0 because of this 1 by t. Okay. So for whichever signal whose energy is finite, the power will always be 0. And when power is greater than 0, that is, we have finite power, the energy will always be infinity. Keep this in mind. And for whichever signal we have a finite power, we call that as power signal. So how we call finite energy to be as how we called signals with finite energy as energy signals, here we call signals with finite power as power signals. Okay, let's see some examples. The rectangular function. So this has finite energy. We know that all these signals that we have here are finite energy. So we should see that their power should be equal to 0. So even before solving this, just by knowing the property, we have now discovered what the power should be. Let's just verify that. So what is the power? 1 by t limit. So this t tends to infinity does not refer to any period. Okay. So don't confuse this t here with the period of the signal. This t refers to some variable which we are changing, right? Because we are letting that t to infinity. So we are just changing the time over which we are taking the average. So this is not referring to the period. Don't get confused with that. So this is minus t by 2 t by 2, the rectangular function mod squared dt. So what is this? So let's say that this is minus t by 2 to t by 2, and this is 1 as long as t is less than 1, or mod t is less than 1. So for all other values, this is 0. Okay, so which means we can say that this is 1 by t times for t less than 1, which is equal to once again for t less than 1. So what happens when t is greater than 1? So if t is greater than 1, so this integral is for t less than 1. For t greater than 1, we have 1 by t times 1. So this integral in that case will exist only between half to minus half. So which gives us 1 by t. Okay. And essentially what we t tends to infinity, 1 by t, which is equal to 0. Okay. So we now saw that the power is equal to 0 for the rectangular function. Now same will be the case for the triangular function, right? So we just computed the energy of the triangular function, right? So in other words, minus t by 2 t by 2 of the triangular function is 2 by 3 as long as this is less than or this is equal to 1 or less than equal to 1. For all other values, so what happens if it is greater than this is equal to 1 by t times 2 by 3 for t greater. So we can use the same technique to find out the power of the rest of the other signals, right? So what was the energy of the triangular signal? We saw that it was 2 by 3. In other words, so minus t by 2 to plus t by 2, the triangular signal's power is nothing but 2 by 3 divided by 3 for t greater than 1, right? Which means as you let the limit tend to infinity, 2 by 3 by t once again is going to be 0. So triangular signal also has power 0, rectangular signal also has power 0. So extending the same case, what about our signal x of t here? So minus t by 2 to plus t by 2, 1 by t. The signal x of t here that we have here will be equal to 4 by 3 by t for mod t greater than 1, the same that we had before. This also implies that px is equal to 0. Same explanation. Now what about this exponential signal? The exponential signal is extending to infinity. So let's see if that makes any difference. So this is 0 on the negative side, so we just have only the positive side. This is 1 by t power minus 2 times 0 minus e power minus t. This is 1 minus e power minus t divided by 2t. So what happens to this as this tends to infinity? So limit t tends to infinity, 1 minus e power minus t by 2t. The numerator goes to 1 because e power minus infinity is 0. Denominator goes to infinity, so we have 1 by infinity form, which is also 0. Okay, so which means all the signals that we have here have power 0. This makes sense because we just saw that any signal which is an energy signal, which has finite energy, will have power to be equal to 0. Doesn't matter if it is finite length or infinite length, and that exactly is happening in these cases. Now let's see the power of some periodic signals. We already said that the periodic signals will have infinite energy, which means they are power signals. Now let us see if they have finite power. So let's see the first case. This is limit t tends to infinity 1 by t integral a square or square omega t dt. Let's first evaluate this integration. Okay. So this integral is a square by t. Call this as, we'll use cos 2 theta formula. So we know that cos 2 theta is 2 cos square theta minus 1, which makes this 1 plus cos 2 omega t by 2. Okay. All right. Now, when we integrate this, there is a very simple way of integrating, because we'll call this as a square by 2t 1 dt plus a square by 2 integral minus t by 2t by 2 cos omega 2t dt. The nice thing about cosine signal is that if you see the signal how it is going to be of this form, right? Which means that whatever is the area here, that area will get cancelled out, and whatever is the area here, that will get cancelled out by this portion. So as long as we are taking t, which is integral multiples of its period, because anyway we are extending t to infinity, we'll always have integral multiples of the period of the cosine signal. So this integral will go to 0, simply because the area under the cosine curve is 0 as long as you are integrating over a full period. Okay, so this integral will go to 0. The only thing that we have here is this integral. So this integral, of course, if you evaluate, you will get a square 2t into t, which is just a square by 2. In other words, we have limit t tends to infinity a square by 2. There is no t here to take limit to, which means the power itself is nothing but a square by 2. Now this is finite, right? As long as the amplitude is finite. Hence, we have a power signal. We saw that the energy of the signal was infinity, but the power is now finite. So we have a power signal. All periodic signals are power signals. Now what about this signal? The first thing to note that is, if omega is not equal to v, we have sum of two orthogonal signals. So if there are two orthogonal signals and you add them up, the energies will add up. The same also applies for power, because power is nothing but average energy. So if the energies add up, the power will also add up. So the power of sum of two signals, if they are orthogonal, is nothing but the sum of their individual powers. So we can use that property here. Okay, and let's see what happens. So we'll first find out the power of one sinusoid. This is limit, same thing that we did before. We'll just take this integration again, 1 by t so we'll use the same formula for sine square, and we get cos 2 omega t by 2 dt. Following the same steps that we did before, we'll get the integral of 1 dt to be the only non-zero value. So this will be equal to a square by 2, and the other integral that we have here will anyway go to 0. this will anyway go to 0. Okay. So which means this power is also equal to a square by 2, which is finite. Now what will be the total power here? So the total power of this is a square by 2 plus b square by 2. Remember, because they are orthogonal. So we have now two power signals which are periodic and hence their energies are 0, but they have finite power. Now let's see another example. So we said the step function is an energy signal which has a. Now we'll see some more examples. We said that the step function has infinite energy, right? So which means we should be able to compute its power. Let's see what the power is. So the power of the step function is 0 to t by 2 1 dt, which is nothing but t by 2 by t, which is half. This does not have any t in it, so limit t tends to infinity 1 by 2 is 1 by 2. So the power of the step function is half. Okay, which makes sense, right? What is the step function? So the step function is just 1 for the positive side of time. This is 1 here, right? So if you take the average energy in any time window, you have only half of that to have any non-zero value. So the power has to be half, because any time window has only half of the duration to be non-zero, the other is 0. Okay, now let's see for e power at minus e power at dt whole squared. This is equal to r at by 2a. This is 1 by 2 at e power a capital T minus e power. So this is what we have. So if we apply the limits here, limit t tends to infinity, 1 e power at minus e power minus by 2 at. If a was positive, let's see what happens. So a is positive, then we have infinity minus 0 divided by infinity. Okay, we get infinity by infinity form. But what you can do is you can take the L'Hopital, and then if you take the L'Hopital, you will get e power at divided by a divided by 2a. Now this goes to infinity. So what about a less than 0? So here we get 0 minus infinity by infinity. Now let's take L'Hopital once again, because we have infinity by infinity form. So if you take L'Hopital, what you get? E power minus at is a minus divided by minus a by 2a. This once again goes to infinity when you apply the limits. Okay, so this means for both positive and negative values of a, we have the power of the signal also to be infinite, not just the energy, but the power also to be infinite. So now we saw signals which have 0 energy, which have finite energy, for which the power is always 0. And we encountered signals which have infinite energy, for which we tried to compute power, and then we saw that it can have finite power. But now we are encountering a signal which can have power also infinite. So there can be signals for which power is also infinite, energy is also infinite. We computed the power for positive values of a and negative values of a. Let's compute the power for imaginary value. So if A is imaginary, let's say J, then the thing that we have to note is we cannot directly integrate e power at as just take a square here, then this is what we were doing so far, right? So we cannot do this for complex numbers, because what we have to keep in mind is to compute the magnitude square of complex numbers, the way that we have to do is take the product of the complex number with its conjugate. This is what that needs to be done in order to compute the magnitude square of complex numbers. So when A is J, then e power at mod square is in fact e power jt times e power minus j. This is how we need to actually compute it. Earlier we just simply said, okay, e power at mod square for real values is nothing but e power 2at, right? This makes sense only for real values of A. If A is complex, then you cannot just simply say the magnitude square is e power 280, and if you integrate this, you will get a different answer, which is not right. So this is how we need to compute magnitude squared for complex numbers. Okay, so what is this magnitude? If you find the complex numbers magnitude, we know that e power jt is a phasor, so the magnitude is obviously going to be 1. This is e power 0 in fact, so it's going to be 1. So what would be the power in this case? The power in this case is 1 by t, integral minus t by 2 to t by 2, 1 dt, which is nothing but 1. Okay, it is 1 because you have 1 by t outside, and the integral's value is t by 2 plus t by 2. So this entire value turns out to be just 1. So now you apply the limit to this, apply limit t tends to infinity. So this term does not contain any t because t gets cancelled. So this power is always 1. So for a complex sinusoid, power is equal to 1. Energy is obviously infinite. So this is a power signal. So if you have observed something so far, all the periodic signals we said are actually containing infinite energy. So they are power signals, they have finite power. So there is also a simpler way to compute the power in periodic signals, which we saw when we computed the power for the sinusoids, cos signal, cos plus sine, and even in fact the complex sinusoid. So what exactly is going on here is, first we compute the energy in one period and then take the average over the time, right? So what is power? Power is basically nothing but average energy, right? So can we just compute the energy of the signal in one period and then just average it over the period's length? Would that be sufficient? It should be sufficient, right? Because we know that periodic signals keep repeating in time forever, right? So if you compute the average in one time duration, let's say you compute the average in this time duration, that should be the average energy present in the signal overall, right? So you can increase the time duration to a different length. So the energy just gets multiplied by 3 because the same copy of the signal is what you have 3 times now. And the time period is also increasing by 3 times. So the energy has increased threefold, time duration has increased threefold. Now you add more copies, so you increase the time duration. Let's say you increase the time duration by 5 periods. Then the energy also increases by 5 times, the period length also increases by 5 times. So there is a direct proportional increase in energy as and when you increase the time period. So which means they get cancelled out, and the only thing that you have is the average energy in one period. So it's easier to compute the power of periodic signals. All you have to do is compute the energy in one period and then average over the period's length. So if somebody asks you to compute the power of a periodic signal, all you do is just compute the energy, okay, in one period. So this is the energy in one period. Energy and then find the average of that over the period length. So because the signal is periodic and the energy in one period keeps repeating in every other period, it's easier to compute the power here. Okay, so keep this in mind. It's always easier to compute the power of periodic signals compared to other power signals. All you have to do is just focus on only one period, and that is enough. That's because we saw a property earlier. Remember, the area of the signal under any time length t is the same. That's in fact the property that we are exploiting here. Just compute the area of the signal squared in one period, and that's enough. That's going to keep repeating again and again. So it's easier to compute the average in this fashion. So in fact, we can use this itself to compute the power of a sinusoid. Let's say a sine omega t or a cos omega t. You will see that we got the same thing.